There's something haunting about the moon's surface when you look closely, not just the familiar seas of dark volcanic plains or the towering mountain ranges, but something far more mysterious. Scattered across its dusty terrain are craters that don't behave the way they should. These aren't your typical impact sites, littered with debris or surrounded by the chaotic aftermath of a collision. No, these are silent, almost pristine, as if time forgot to touch them. 31 of these enigmatic formations exist, each one a perfect imprint with no scattered rubble, no telltale signs of the violent events that created them. It's as if the moon decided to keep some of its scars a secret, leaving scientists scratching their heads and sparking questions that challenge everything we thought we knew about lunar geology. What could cause a crater to form without leaving behind the usual mess? It's like dropping a rock into a pond and expecting no ripples. It defies logic. Yet here they are, these ghostly fingerprints, scattered across the moon's surface, each one a puzzle waiting to be solved. Some theories suggest these impacts might have happened in a way that minimized debris, or perhaps the material ejected simply vanished into the vacuum of space. Others wonder if the moon's surface behaved differently in these spots, absorbing the shock in a way we've never seen before. The more we learn, the clearer it becomes. These craters aren't just oddities, they're clues pointing to hidden chapters in the moon's turbulent history. This is the kind of mystery that reminds us how much we still have to discover, even in our own cosmic backyard. The moon has been Earth's silent companion for billions of years, yet it holds secrets that continue to surprise us. Today, we're going to explore these 31 silent craters, diving into the latest research, the most compelling theories, and the unanswered questions that keep scientists up at night. By the end of this journey, you'll see the moon in a whole new light, not just as a familiar sight in the night sky, but as a world with stories still waiting to be told. So let's begin, because the truth behind these eerie craters is stranger than anything we could have imagined. The moon's surface is like a vast, dusty history book, each crater a sentence written in the language of cosmic violence. Most tell a familiar story: meteorites slamming into the surface, sending debris flying in all directions, leaving behind jagged rims and rough, scattered ejecta. But these 31 silent craters, they're the outliers, the pages torn cleanly from the book. No rubble, no chaos, just smooth, undisturbed bowls carved into the lunar terrain as if by an invisible hand. What's even more baffling is how they defy the basic rules of impact physics. When a space rock hits the moon, the energy of that collision doesn't just vanish, it ripples outward, fracturing the surface and flinging material for miles. So why don't these craters follow the script? One possibility is that something about the moon's subsurface in these specific spots absorbed the shock differently. Imagine dropping a hammer onto a pillow instead of concrete. The energy dissipates quietly, leaving no trace. Some researchers think pockets of loosely packed regolith or even hidden layers of volatile material beneath the surface could have cushioned the blow, swallowing the violence of the impact before it could leave its usual messy signature. Then there's the eerie possibility that these craters are far younger than they appear. If an impact happened during a period when the moon's surface was covered in a temporary, dense layer of dust or gas, perhaps from volcanic activity or a passing comet's tail, the ejected material might have settled back almost instantly, erasing any trace of the collision. It's like throwing a stone into thick mud. The splash collapses inward, leaving barely a ripple. But the most tantalizing theory involves the moon's hidden magnetism. Strange, localized magnetic fields have been detected near some of these craters, raising the question: Could these invisible forces have somehow guided or altered the way debris was scattered? It's a long shot, but in the world of lunar mysteries, even the wildest ideas deserve a closer look. One thing's for sure, these silent craters aren't just quirks of geology. They're windows into processes we're only beginning to understand. And with every new lunar mission, we get one step closer to reading their secrets. Silent impact craters don't just defy expectations, they rewrite the rules. Picture a typical lunar crater: jagged edges, a chaotic spray of debris fanning outward, a scar left by cosmic violence. Now imagine its opposite, a smooth, bowl-shaped depression with no surrounding rubble, no fractured terrain, almost as if the impact never happened. That's the enigma of these formations. They're not just rare, they're architectural anomalies, like perfectly placed scoops taken out of the moon's surface with surgical precision. So what sets them apart? One leading theory points to the angle of impact. Most meteorites strike at steep angles, blasting material outward in all directions. But if an object hits at an extremely shallow angle, almost skimming the surface, the energy might dissipate differently, minimizing debris. Think of skipping a stone across a pond. The ripples are gentle, the splash contained. On the moon, a grazing impact could leave behind a clean, symmetrical crater with little to no ejecta. Then there's the lunar regolith itself, the layer of dust and broken rock covering the moon's surface. In some regions, it might behave like a cosmic shock absorber. If the regolith is unusually loose or deep, it could swallow the force of an impact, preventing the usual explosive scatter. It's like dropping a heavy ball into a pit of fine sand. The energy disperses quietly, leaving no mess behind. But the most intriguing possibility involves something far more elusive: the moon's hidden geology. Beneath its dusty exterior, the moon might harbor pockets of volatile compound substances that vaporize on impact, leaving no trace. If a meteorite struck one of these hidden reservoirs, the resulting explosion could be more like a muffled pop than a violent blast, with the ejected material settling back into place almost instantly. And let's not forget time. The moon's surface has endured billions of years of bombardment, erosion from micrometeorites, and the relentless pull of solar radiation. Could these silent craters simply be older formations, their debris long since erased by the slow sandblasting of space? Or are they evidence of a process we've yet to understand? What's clear is that these craters aren't just oddities, they're invitations to rethink how celestial bodies record their history. Every pristine crater is a question, a challenge to our assumptions about the moon's past. And as we uncover more of these silent witnesses, we're not just solving a lunar mystery, we're decoding the hidden language of impacts written across the cosmos. The moon's dusty skin holds secrets that could explain these ghostly craters, secrets buried in its regolith, that strange, otherworldly soil unlike anything on Earth. Imagine walking across a beach where the sand doesn't shift underfoot but instead clings together, behaving more like flour than loose grains. That's lunar regolith, a layer of fine, pulverized rock and glass forged by eons of meteorite strikes and solar radiation. It's this peculiar material that might hold the key to why some impacts leave no trace. When a meteorite slams into Earth's surface, the ground reacts predictably, rocks fracture, soil sprays outward, and debris fans into familiar patterns. But the moon's regolith plays by different rules. In some areas, it's loose and fluffy, like freshly fallen snow. In others, it's densely packed, almost cement-like, fused by the heat of ancient impacts or the pressure of overlying layers. If a space rock strikes one of these compacted zones, the energy might not explode outward in a chaotic spray. Instead, it could dissipate inward, absorbed by the regolith's cohesive structure like a punch landing on a foam pad. Scientists have even simulated these impacts in labs, dropping projectiles into trays of artificial lunar soil. The results are startling. Under the right conditions, the soil can swallow the impact's energy whole, leaving behind a clean depression with no ejector. It's as if the regolith acts like a cosmic sponge, soaking up the violence before it can leave a mark. Some researchers speculate that electrostatic forces, the same static cling that makes lunar dust stick stubbornly to astronaut suits, might help bind the regolith together, adding an invisible layer of cohesion that traps debris before it can escape. Then there's the wild card, buried ice. Recent orbital scans suggest pockets of water ice lurk in permanently shadowed craters near the moon's poles. If an impact struck a region where ice mingled with regolith, the sudden heat could vaporize the ice instantly, creating a cushion of gas that muffles the collision. Picture dropping a firecracker into wet sand. The explosion is muted, the sand collapsing back into place with barely a disturbance. But here's the twist: not all silent craters sit in these special zones. Some appear in regions where the regolith should behave normally, leaving scientists puzzled all over again. Could there be another layer to this mystery, something beneath the surface we haven't detected yet? The more we study these eerie formations, the clearer it becomes. The moon's dust isn't just a passive blanket. It's an active player in shaping these craters, and its secrets are still unfolding. The angle at which a meteorite strikes the moon isn't just a minor detail, it's a game changer. Most impacts come crashing down at steep angles, like a diver plunging into deep water, sending shockwaves and debris erupting in all directions. But when a space rock arrives at a shallow angle, almost skimming the surface like a stone skipping across a pond, the physics shift dramatically. Instead of a chaotic explosion, the energy spreads laterally, carving out elongated or asymmetrical craters with far less ejecta. It's the difference between slamming a hammer straight into clay versus dragging it sideways. The mark left behind is cleaner, more subdued. This could explain why some of the moon's craters appear eerily pristine. A grazing impact might scatter less material, leaving behind a smooth depression with minimal rubble. But here's the catch: while shallow angles can reduce debris, they don't typically erase it entirely. Those 31 silent craters take this phenomenon to the extreme, showing no ejecta at all, no scattered boulders, no telltale rays of dust, nothing. If angle alone isn't the full answer, what else could be masking the evidence? One clue might lie in the moon's invisible forces. Electrostatic effects, for instance, could play a hidden role. Lunar dust is famously clingy, levitating and sticking to surfaces due to static charges from relentless solar radiation. If an impact occurred in a region where these electrostatic forces were unusually strong, could they have pulled ejected material back down, effectively vacuuming up the debris before it could settle far from the crater? It's a tantalizing idea, like throwing confetti into a room with a hidden magnet, only to watch it snap back into place. Then there's the moon's subterranean secrets. Beneath its dusty facade, the lunar crust is a patchwork of ancient lava flows, fractured bedrock, and pockets of volatile materials. If a meteorite struck a zone where the subsurface was unusually porous or layered with loosely bonded rubble, the impact's energy might have dissipated inward, muffled like a shout into a pillow. Alternatively, hidden faults or caverns could have swallowed ejected material, collapsing back into the void before it reached the surface. But the most intriguing possibility: these craters might not be solo acts. Could a series of overlapping impacts, each one disturbing the ejecta of the last, have effectively erased their own traces over time? Imagine building a sandcastle. only for each new wave to smooth away the footprints left by the previous one. On the Moon, where billions of years of bombardment have reshaped the landscape, such a process could leave behind a crater that looks deceptively untouched. What's clear is that no single theory fits all 31 of these enigmatic formations. Each one might be a unique puzzle, shaped by a combination of angle, terrain, and forces we're only beginning to understand. And as lunar missions continue to map the Moon's surface in unprecedented detail, we're inching closer to unraveling the truth behind these silent scars, one cryptic crater at a time. The Moon's hidden troves of water ice and volatile compounds might hold the key to understanding these ghostly craters. Beneath its barren surface, the Moon conceals pockets of frozen water, particularly in permanently shadowed regions near the poles, where temperatures plunge so low that ice can persist for billions of years. When a meteorite slams into one of these icy zones, the sudden release of energy doesn't just fracture rock, it flash vaporizes the ice, turning it instantly into gas. This rapid phase change could dramatically alter the physics of the impact. Instead of debris being violently ejected outward, the expanding gas might act like a cushion, absorbing the shockwave and pulling ejected material back into the crater. Picture tossing a firework into a snowbank. The explosion is muffled, the snow collapsing inward rather than scattering. But water ice isn't the only player here. The Moon's subsurface is also laced with volatile compounds, substances like carbon dioxide, methane, or even ammonia that vaporize easily under heat. If an impact hits a volatile, rich patch, the resulting explosion could be more of a fizzle than a bang. The energy would go into vaporizing these compounds rather than launching debris, leaving behind a remarkably clean crater. It's like punching a bag of flour versus a bag of baking soda. One sends particles flying, while the other dissipates with barely a trace. This raises a tantalizing possibility. These silent craters might not just be geological oddities, they could be signposts pointing to hidden lunar resources. If we can map where these pristine formations cluster, we might uncover prime locations for future lunar bases, where water ice could be mined for drinking, oxygen, or even rocket fuel. Suddenly, these mysterious craters aren't just scientific puzzles, they're potential gold mines for human exploration. Yet the plot thickens. Not all silent craters sit in these volatile, rich zones. Some appear in regions where no ice or gases should exist, forcing scientists to reconsider. Could there be other, even more exotic materials beneath the surface that behave similarly? Or perhaps the Moon's ancient volcanic past left behind pockets of porous rock that absorb impacts like a sponge? Every unanswered question pulls us deeper into the enigma, reminding us that the Moon's story is far from fully written. As robotic probes and future crewed missions continue to probe the lunar surface, each new discovery peels back another layer of this mystery. These silent craters aren't just scars, they're whispers from a hidden world, clues to processes we're only beginning to grasp. And with every clue, we're not just solving a lunar riddle, we're learning how to read the secrets of our entire solar system. The Moon's silence isn't just about missing sound, it's about missing air. Without an atmosphere to buffer its surface, the lunar environment becomes a playground for invisible forces, and one of the most surprising players is static electricity. Unlike Earth, where moisture and air currents neutralize charged particles, the Moon's dust is left to fend for itself under the relentless bombardment of solar radiation. Over time, these tiny grains become electrically charged, clinging together with an otherworldly tenacity. Astronauts who walked on the Moon during the Apollo missions quickly discovered this eerie property. Dust clung to their suits like stubborn glitter, refusing to be brushed away. But this electrostatic cling might do more than annoy explorers. it could fundamentally alter how craters form and preserve their aftermath. Imagine an impact sending a plume of debris arcing into the black sky. On Earth, gravity and air resistance would quickly pull those particles back down in predictable patterns. But on the Moon, with no atmosphere to slow them, the dust is at the mercy of electrostatic forces. If the surrounding terrain carries an opposite charge, those ejected particles might not travel far before being yanked backward, like iron filings drawn to a magnet. The result, a crater that looks eerily clean, as if the debris never left. Some researchers even speculate that electrostatic dust fountains could loft material high above the surface, only for it to settle back into the crater bowl, erasing traces of the impact entirely. Laboratory experiments here on Earth offer tantalizing clues. Scientists have recreated lunar conditions in vacuum chambers, charging simulated regolith and observing how it behaves. Under the right conditions, charged dust particles don't just fall, they drift, forming dense clouds that could theoretically redistribute ejecta in ways we're only beginning to understand. It's a phenomenon unlike anything we see on our planet, where gravity alone dictates where debris lands. But here's where the mystery deepens. Not all of the Moon's silent craters sit in regions with strong electrostatic activity. Some appear in areas where charging should be minimal, suggesting this force might only be part of the puzzle. Could electrostatic effects combine with other factors like subsurface composition or impact angle to create these pristine formations? Or is there another, even stranger process at work? What's clear is that the Moon's dust isn't just passive scenery, it's an active participant in shaping these enigmatic craters. And as we prepare to return to the lunar surface with new missions, we might finally get the chance to study these electrostatic quirks up close. Every speck of dust clinging to a rover's wheels, every strangely smooth crater rim, could hold the key to unraveling one of the Moon's quietest mysteries. If you placed a silent crater side by side with a typical lunar impact site, the differences would stop you in your tracks. Picture a classic meteorite crater, jagged, uneven edges, with rays of ejected material stretching outward like the spokes of a wheel. Now look at its silent counterpart, a smooth, bowl-shaped depression with crisp, defined borders, as if someone pressed a giant spoon into the Moon's surface. The contrast isn't just striking, it's a scientific goldmine, offering clues to the forces that shaped these anomalies. Traditional craters tell a violent story. When a meteorite strikes, the explosion flings debris in all directions, creating secondary craters where larger chunks of ejecta crash back down. The surrounding terrain becomes a chaotic mess of fractured rock and scattered dust, with radial patterns stretching for miles. But silent craters, they're like whispers in comparison. No secondary impacts, no rays of debris, just a single, undisturbed imprint. It's the difference between a bomb going off and a feather landing in sand. So why such a dramatic disparity? One key factor might be the speed of the impacting object. High-velocity collisions generate tremendous heat, melting rock and vaporizing material, which then sprays outward in explosive plumes. But if a meteorite arrived at lower speeds, perhaps slowed by an oblique approach or a lucky gravitational nudge, the impact could be more like a slow-motion push, carving out a clean depression without the usual fireworks. Then there's the Moon's subsurface. Traditional craters often form where the crust is rigid, shattering like glass under a hammer blow. Silent craters, though, might sit atop hidden layers of loose, unconsolidated material that absorbs the shock like a memory foam mattress. Recent radar scans from lunar orbit have revealed pockets of surprisingly fluffy regolith in some of these areas, lending weight to the idea that the Moon's underground isn't uniform. It's a patchwork of textures, each reacting differently to cosmic collisions. But the most compelling clue might come from age. Most traditional craters are relatively young in geological terms, their debris still fresh on the surface. Silent craters, on the other hand, could be ancient, so old that the relentless rain of micrometeorites has sanded away their ejecta, leaving behind only the smoothest remnants. Think of it like an old scar fading over decades while a fresh wound still stings and scabs. Yet even this explanation doesn't fit all the evidence. Some silent craters appear in regions where erosion shouldn't have erased their debris so completely, suggesting another layer to the puzzle. Could there be a combination of factors at play: angle, speed, subsurface composition, and time, all converging to create these eerily perfect formations? Every silent crater is a snapshot of a moment when the moon's rules of geology bent, offering a glimpse into processes we're only beginning to decode. And as we compare them to their more chaotic cousins, one thing becomes clear: the moon's surface isn't just a record of violence, it's a tapestry of mysteries woven with threads we're still learning to follow. Space weather isn't just a backdrop, it's a sculptor, tirelessly reshaping the moon's surface one microscopic grain at a time. Solar wind, a relentless stream of charged particles from the sun, and the constant peppering of micrometeorites act like cosmic sandpaper, eroding and darkening the lunar landscape over millions of years. Most craters bear the scars of this slow-motion assault, their once sharp rims softening, their bright ejecta fading into the surrounding terrain. But the silent craters, they stand apart, defying the inevitable march of decay. Their crisp edges and undisturbed bowls look almost untouched, as if time skipped over them entirely. This defiance of space weathering raises two compelling possibilities. First, these craters might be far younger than their counterparts, formed recently enough that solar wind and micrometeorites haven't had time to blur their features. Imagine two footprints in wet sand, one made an hour ago, the other just seconds before the tide rolls in. The older one would already show signs of erosion, while the newer might still look pristine. If silent craters are the moon's fresh footprints, their youth could explain their unweathered appearance. Lunar missions like NAS, a lunar reconnaissance orbiter, have clocked some of these formations at ages far younger than the surrounding terrain, hinting at a timeline that sidesteps eons of exposure. But there's another, even stranger idea. What if these craters aren't just young? What if they're inherently resistant to erosion? The moon's surface isn't uniform. Some materials weather faster than others. Compacted regolith, for instance, might erode more slowly than loose dust, while mineral compositions could react differently to solar wind. If silent craters formed in regions where the surface was unusually dense or chemically inert, they could weather at a glacial pace, preserving their sharp outlines long after other craters have blurred into obscurity. Then there's the wild card: electrostatic shielding. As solar wind bombards the moon, it charges the surface, creating invisible electric fields that can repel further particles. If silent craters sit in zones where these fields are unusually strong, they might deflect some of the weathering forces, like an umbrella in a sandstorm. It's a fringe theory, but in the absence of a clear answer, even the unconventional deserves a look. What's certain is that these craters aren't just passive victims of time, they're active puzzles, challenging our assumptions about how celestial surfaces evolve. Whether they're young, resistant, or protected by some unseen force, their defiance of space weathering is a clue waiting to be decoded. And as we study them, we're not just unraveling lunar history, we're learning how planets and moons across the universe weather their age. Of all the moon's silent craters, none captivates scientists quite like Giordano Bruno. Perched on the lunar far side, this 30-kilometer wide scar is a paradox, a crater born from what should have been a cataclysmic impact, yet surrounded by none of the chaos you'd expect. Most craters its size are framed by sprawling debris fields, like shattered glass radiating outward. But Giordano Bruno sits in eerie solitude, its bowl smooth and its surroundings unsettlingly clean. It's as if the moon itself hit the mute button on this collision, leaving researchers scrambling to explain the silence. The prevailing theory points to youth. Unlike ancient craters worn down by eons of space weathering, Giordano Bruno's sharp features suggest it might be astonishingly young, possibly less than 1,000 years old. Historical records even hint at its creation. Medieval monks in England reported seeing a fiery flash on the moon in June 1178, an event that could align with this crater's formation. If true, it would make Giordano Bruno one of the freshest large impacts in the solar system, a blink of an eye in geological time. But youth alone doesn't solve the puzzle. Even a recent impact should have left behind some debris, so where did it all go? One radical idea involves the moon's hidden voids. Beneath its surface, the moon is thought to harbor vast networks of collapsed lava tubes and caverns, remnants of its volcanic past. If Giordano Bruno's impactor struck directly over one of these hollow spaces, the ground beneath might have imploded, swallowing ejected material before it could reach the surface. Picture dropping a bowling ball onto a trampoline covering a pit. The ball vanishes and the fabric snaps back, leaving almost no trace. Then there's the wild card, electrostatic trapping. The moon's dust is notorious for its clinginess, and if the impact occurred during a period of intense solar activity, charged particles might have magnetically pulled debris back into the crater. It's a fringe idea, but in the absence of conventional explanations, even the unconventional gets a seat at the table. What makes Giordano Bruno so compelling isn't just its mystery, it's the way it challenges our understanding of lunar geology. Most craters fit neatly into categories, old or young, messy or clean. But this one defies classification, forcing scientists to rethink the rulebook. Could it be a hybrid shaped by both impact and collapse, or is it a sign of processes we've yet to discover? Every new lunar mission brings us closer to answers, but for now, Giordano Bruno remains a riddle wrapped in moondust, a silent witness to the moon's untold secrets. NASA Lunar Reconnaissance Orbiter has given us eyes sharper than Earth's mightiest telescopes, peering down at the moon's silent craters with an almost surgical precision. What it's revealed is astonishing. These enigmatic formations aren't just lacking debris, their floors are polished to an unnatural smoothness, like glass under a jeweler's loupe. This isn't the rough texture you'd expect from a violent cosmic collision. It's something far more deliberate, as if unseen hands have been tirelessly sanding these craters from the inside out. The orbiter's high-resolution cameras have spotted something even stranger: tiny, intricate cracks spiderwebbing across some crater floors. At first glance, they might look like ordinary fractures, but their patterns tell a different story. These cracks resemble the fine lines you'd see in drying mud or cooling lava, hinting that the crater floors might have once been molten or plastic, slowly settling into their current smooth state. Could residual heat from the impact have melted the underlying rock, creating a temporary liquid layer that oozed back to erase all traces of debris? It's a radical idea, but the evidence is right there in the image's craters that didn't just form, but healed. Then there's the puzzle of the ghost halos. Some silent craters are surrounded by faint, circular discolorations in the regolith, invisible to the naked eye, but glaringly obvious under the orbiter's sensitive instruments. These halos might be the last whispers of ancient ejecta, so thoroughly pulverized by micrometeorites over millennia that they've dissolved into the surrounding dust. It's like finding a water stain long after the glass has been removed. The event left its mark, but the evidence has all but vanished. But the most startling discovery comes from the orbiter's thermal measurements. While most lunar craters show predictable temperature variations, cold at night, blistering by day, some silent craters have floors that stay suspiciously even-keeled. This thermal inertia suggests their surfaces might be packed unusually tight, with grains of regolith bonded together in ways we've never seen before. Imagine the difference between stepping on fresh snow versus icy pavement. One crumbles, the other holds firm. If these crater floors have naturally cemented over time, that could explain why they've resisted the erosive forces that rough up typical impact sites. What's emerging from this data is a picture far more complex than we imagined. These aren't just craters that happen to stay clean, they're active geological puzzles, shaped by processes we're only beginning to decipher. Whether it's hidden melting, electrostatic cementing, or some unseen lunar weathering mechanism, each new image from the orbiter pulls back another layer of the mystery. And with every revelation, we're not just learning about the moon, we're rewriting the textbook on how planetary surfaces evolve. Beneath the moon's dusty surface lies a hidden network of tunnels, relics of its volcanic past, when rivers of molten rock carved channels through the crust. Over time, some of these lava tubes collapsed, leaving behind long, winding cavities just beneath the regolith. Now, scientists are asking a provocative question. Could these subterranean voids be the reason some craters appear eerily silent? Imagine a meteorite slamming into the moon's surface directly above one of these hollow tubes. Instead of debris exploding outward, the impact might punch through the ceiling, sending rubble tumbling into the darkness below. The result, a crater with no ejector, just a clean, bowl-shaped depression where the material simply vanished into the moon's hidden underworld. It's like dropping a rock onto a wooden bridge with rotten planks. The rock doesn't bounce back, it falls straight through, leaving barely a trace. This theory gained traction after orbital radar scans revealed strange, funnel-shaped anomalies beneath some silent craters' features that look suspiciously like collapsed lava tubes. But proving the connection isn't easy. Without direct exploration, it's hard to say whether these voids are empty chambers or just dense, fractured rock that absorb the impact's energy differently. The intrigue doesn't stop there. Some silent craters have floors that appear slightly sunken, as if the ground sagged after the impact. Could this be a sign of subsurface cavities slowly collapsing under their own weight? Or might volcanic gases, trapped for eons, have escaped during the collision, muffling the explosion like a cork popping from a champagne bottle? Future missions could hold the key. Rovers equipped with ground-penetrating radar or even small seismic probes could map these underground labyrinths in detail, revealing whether they're truly the missing piece of the silent crater puzzle. Until then, the idea remains a tantalizing possibility, one that reminds us just how much of the moon's story is still written in the shadows. When a space rock slams into the moon at cosmic speeds, the energy of that collision doesn't just fracture rock, it can turn solid ground into liquid in an instant. This phenomenon, known as impact melting, might hold the key to understanding some of the moon's eerily clean craters. Picture a bullet striking a block of ice. The immediate area around the impact doesn't just crack, it liquefies, then refreezes into a smooth, glassy patch. On the moon, that same process could explain why certain craters look like they've been polished from the inside out. Their floors unnaturally smooth compared to the rough, debris-strewn landscapes around them. Laboratory experiments here on Earth have recreated these extreme conditions, firing projectiles into lunar soil simulants at blistering speeds. The results are striking. At the moment of impact, temperatures can soar high enough to melt silicate rock, creating a molten pool that cools into a glassy veneer. This self-sealing effect could trap debris beneath the surface, preventing it from scattering outward. It's like slapping a spoon into thick pudding. The initial splash is contained as the liquid settles back into place, leaving little trace of the disturbance. But the real smoking gun comes from actual lunar samples. Apollo astronauts brought back fragments of impact glass, tiny beads of once molten rock forged in the heat of ancient collisions. Under microscopes, these beads reveal a telltale smoothness, their surfaces unmarred by the abrasive forces that roughen typical lunar soil. Some silent craters could essentially be vast versions of these glassy droplets, their entire floors transformed into natural mirrors by the fury of their creation. There's a catch, though. Not all high-energy impacts produce these pristine results. The angle of collision matters melting tends to be most intense when meteorites strike head-on, concentrating their energy into a smaller area. The composition of the target also plays a role. Certain minerals melt more readily than others, and pre-existing fractures in the bedrock can channel heat away unevenly. This might explain why some craters in similar regions look radically different, one glassy and silent, its neighbor a jagged mess of rubble. The most fascinating implication. Impact melting could create temporary lava lakes in these craters, miniature versions of the Moon's ancient volcanic seas. As the molten rock cools, it might contract, forming those intricate crack patterns seen in orbital images like mud drying in the sun, but on a planetary scale. This process wouldn't just erase debris, it would actively remodel the crater's interior, sculpting it into something unnaturally smooth. Yet even this compelling theory doesn't fit every silent crater. Some show no signs of melting at all, their floors made of ordinary regolith. Others are too large for the melting explanation to hold. Their energy would have vaporized material entirely, leaving a different kind of scar. So while impact melting might solve part of the puzzle, it's clear the Moon has more than one way to keep its craters quiet. Each glassy depression is a reminder of the incredible forces at work in our solar system and the mysteries that still linger just beneath the surface. The Moon's crust isn't just a blank slate, it's a patchwork of geological personalities, each with its own quirks. Some regions are dense and unyielding, like granite countertops, while others crumble like stale bread under pressure. When a meteorite strikes these different zones, the results couldn't be more dramatic. Hit a dense, solid patch, and the impact sends shockwaves racing outward, shattering the surface into a chaotic spray of debris. But land in a softer, more porous area, and the energy might simply vanish, swallowed whole by the ground beneath. This stark contrast could explain why some craters emerge pristine while others look like cosmic demolition sites. Take the Moon's highlands, for example. These ancient, rugged landscapes are packed with anorthosite, a tough, light-colored rock that's stubbornly resistant to erosion. When impacts occur here, they tend to leave classic debris-filled craters, the kind we're used to seeing. But venture into the Lunar Maria, those vast, dark plains of solidified lava, and the story changes. Basalt, the volcanic rock that dominates these regions, is riddled with tiny pores and fractures from its violent origins. An impact here might behave like a hammer striking a sponge. The energy disperses inward, muffling the explosion and minimizing ejecta. Then there's the wild card, Brexia. This Frankenstein's monster of lunar geology is a jumble of shattered rock fragments, fused together by the heat of ancient impacts. In some areas, Brexia forms layers so loose and unconsolidated that they act like shock absorbers. A meteorite slamming into one of these zones could sink its energy into rearranging the chaotic rubble beneath, rather than blasting material skyward. It's the difference between kicking a solid wall, ouch, and kicking a pile of laundry. One leaves your foot throbbing, the other just swallows the impact with a dull thud. Recent orbital surveys have added a fascinating twist to this puzzle. Silent craters aren't randomly scattered, they cluster in specific regions, like shy guests at a cosmic party huddling in the same corner. By overlaying geological maps with crater locations, scientists have spotted tantalizing patterns. Some clusters align with areas where the moon's crust is unusually thin, or where volcanic vents once spewed gas-rich lava. Others sit atop hidden fault lines, where the ground might already be pre-fractured and prone to absorbing impacts quietly. But the real breakthrough could come from studying the moon's magnetic anomalies. Strange, localized magnetic fields ripple across certain regions, and some silent craters sit squarely within these invisible zones. Could magnetism somehow alter the way debris behaves post-impact? It's a long shot, but on the moon, even the wildest ideas deserve a second look. Every new orbital scan, every rover's ground-penetrating radar sweep brings us closer to decoding the silent crater enigma, one geological clue at a time. What's clear is that the moon's crust isn't just a passive canvas for impacts. It's an active participant, shaping each crater's fate through hidden variations in density, structure, and chemistry. And as we piece together this subterranean mosaic, we're not just solving a lunar mystery, we're learning how planetary surfaces everywhere record their violent histories, one silent scar at a time. The moon doesn't just hide silent craters, it's a treasure chest of unexplained anomalies, each one whispering a different secret. Take its magnetic quirks, for example. Unlike Earth, which has a global magnetic field generated by its churning core, the moon's magnetism is patchy and unpredictable. Yet some of these mysterious magnetic zones overlap eerily with silent craters, as if invisible forces are at work beneath the surface. It's not just coincidence, it's a clue. Could these localized magnetic fields have somehow redirected debris during impact, pulling ejected material back like cosmic magnets? Or do they hint at something deeper, ancient volcanic activity or metallic deposits that altered the way these craters formed? Then there's the moon's gravitational oddities. Orbiting probes have mapped regions where gravity weakens or strengthens inexplicably, creating what scientists call mass concentrations, or mascons. These hidden pockets of dense material warp the moon's gravitational field, subtly tugging on spacecraft overhead. And guess where some of the most prominent mascons lurk? Beneath basins that also host silent craters, the connection is too tantalizing to ignore. If an impact struck one of these mascon regions, the dense subsurface material might have absorbed the shock differently, muffling the explosion and minimizing debris. Picture dropping a weight onto a trampoline, landed on a reinforced patch, and the bounce vanishes. But the anomalies don't stop there. Infrared scans have revealed hotspots, areas where the lunar surface retains heat unusually well, even during the frigid lunar night. Some of these thermal oddities line up with silent craters, suggesting their floors might be made of materials that conduct or retain heat in bizarre ways. Could these hotspots be the aftermath of impact melting, where molten rock cooled into glassy, heat-trapping surfaces? Or do they point to lingering volcanic activity, with residual warmth still seeping from cracks in the crust? The most compelling thread tying these anomalies together, time. Many silent craters, magnetic zones, and mascons cluster in regions shaped by the moon's most violent epoch, the period billions of years ago when volcanic floods and colossal impacts reshaped its surface. If these events left behind pockets of unusual rock, buried lava flows, or even subterranean voids, they could have set the stage for the anomalies we see today. A silent crater might not just be a single mystery, it could be the echo of a much older, much stranger lunar drama. What's clear is that these craters aren't isolated puzzles. They're pieces of a larger enigma, one that stretches from the moon's magnetic whispers to its gravitational murmurs. And as we connect the dots between them, we're not just solving a lunar riddle, we're decoding the hidden language of planetary evolution itself. The idea that silent craters might be artificial, perhaps the work of some long-lost lunar civilization, makes for thrilling science fiction. But when we shift from speculation to hard evidence, the scientific consensus is clear. These formations are entirely natural, shaped by forces we're still working to understand. That doesn't make them any less fascinating. In fact, the truth behind these craters is stranger than any conspiracy theory. Take the myth that their perfect symmetry hints at intelligent design. Nature is full of symmetrical patterns, snowflakes, honeycombs, even the orbits of planets. Silent craters achieve their smooth shapes through the same universal laws of physics, just under rare and specific conditions. Their geometry isn't a signature of engineers. It's a testament to how energy dissipates when certain variables align: angle, speed, and subsurface composition, all playing their part. Another persistent claim is that the lack of debris points to deliberate cleanup, as if some unseen hand swept away the evidence. But the moon's environment offers plenty of natural explanations. Electrostatic forces can pull dust back into craters, while hidden voids or volatile rich soil might swallow ejecta whole. Compare it to a desert sand dune reshaping itself in the wind. No one accuses the wind of having an agenda. The moon's surface is dynamic in its own quiet way, constantly rearranged by forces we're only beginning to measure. Then there's the notion that these craters cluster in suspiciously precise arrangements. In reality, their distribution follows geological trends, not architectural blueprints. They're found near ancient lava flows, thin crustal zones, or areas with unusual magnetic signatures, all markers of the moon's violent past, not alien construction sites. If anything, their patterns reveal how planetary surfaces evolve under bombardment, not how they're built by design. So why does the artificial theory persist? Partly because the unknown invites imagination. Silent craters challenge our expectations, and when science doesn't yet have all the answers, myths rush to fill the gap. But that's also what makes them so valuable to researchers. Every unconventional feature forces us to question assumptions, test new models, and dig deeper into the moon's complex history. The real story isn't about hidden builders, it's about how nature, given the right conditions, can create phenomena that seem impossibly precise. And that's far more awe-inspiring than any fiction. These craters aren't puzzles to solve with wild guesses. They're invitations to explore the boundaries of what we know. And as lunar missions uncover more data, the line between mystery and understanding keeps shifting, revealing a moon that's every bit as surprising as we once dreamed, but undeniably, wonderfully real. Determining the age of the moon's silent craters is like trying to read a book with half the pages glued together. The usual clues just aren't there. On most lunar impact sites, scientists can estimate age by studying the debris field. Younger craters have sharp, bright ejecta that hasn't yet been darkened by space weathering, while older ones fade into the background like weathered tombstones. But silent craters, they're blank slates, they're pristine bowls offering no scattered material to analyze, no rays of ejecta to track. It's a detective story where the evidence has literally vanished. So how do researchers piece together their history? One method involves studying cross-cutting relationships, the geological equivalent of checking which layer of paint came first. If a silent crater slices through an older fracture or lava flow, it must be younger than those features. Conversely, if a fresh crack or smaller impact overlaps its rim that sets a minimum age. It's painstaking work, like reconstructing a timeline from faint pencil marks in a margin. Then there's the subtle art of crater counting. The moon's surface is pockmarked with impacts of all sizes, and statistically, older areas accumulate more small craters over time. By mapping the density of tiny pits around a silent crater, scientists can infer whether it sits in an ancient or relatively young terrain. But this approach has limits. What if the silent crater formed in a region already saturated with old impacts? The numbers blur, leaving room for debate. New technologies are shaking up the field. Laser altimetry from orbiters like NAS, a lunar reconnaissance orbiter, can detect microscopic changes in surface texture, revealing hints of erosion that might correlate with age. Meanwhile, spectrometers analyze mineral compositions in crater walls. Certain minerals degrade predictably under solar radiation, acting as cosmic clocks. And then there's the game changer, in situ sampling. Future missions could land near these craters, drilling into their rims to study radiation exposure levels in individual grains, a technique that's transformed dating on Earth's own impact sites. But the real breakthrough might come from an unexpected source, the moon's magnetic memory. Some rocks retain traces of the magnetic field present when they formed. If silent craters excavated material from deep underground, their walls could preserve a snapshot of the moon's ancient magnetic activity, offering indirect clues to their age. It's a long shot, but in lunar science, even fringe ideas can lead to revelations. What's clear is that these craters refuse to give up their secrets easily. Every workaround, every innovative work of dating them peels back another layer of complexity. And with each challenge, we're not just solving a lunar puzzle, we're rewriting the rules of how to read a planetary surface where the usual clues don't apply. The next chapter in unraveling the moon's silent craters won't be written from orbit, it'll be etched into the lunar soil itself by boots and rover treads. NASA Artemis program, along with international missions from China, India, and private ventures, is poised to turn these enigmatic formations from distant curiosities into hands-on laboratories. Imagine a rover rolling up to one of these eerily smooth depressions, its instruments scanning not just the surface but the very atoms beneath. For the first time, we could press a drill bit into that unnaturally pristine floor, extracting cores that reveal whether the ground melted and recooled, whether hidden gases escaped, or if electrostatic forces really did glue the debris back into place. But the real game changer, human eyes on the ground. Astronauts trained in field geology notice what machines might miss, the subtle crack patterns hinting at ancient heat, the way dust behaves when disturbed, even the faintest discoloration in the regolith that could betray a crater's hidden history. Picture an Artemis astronaut kneeling by Giordano Bruno's rim, chipping a sample from its glassy floor. Back on Earth, labs with atomic-level precision could analyze those samples for isotopes that act as cosmic clocks, pinpointing the impact's exact age, or for minerals altered by processes we've never seen firsthand. Then there's the tech revolution quietly reshaping lunar exploration. Next-gen rovers like Japan's SLIM or ESA's Prospect carry ground-penetrating radars capable of mapping subsurface voids without digging, finally testing the lava tube theory. Meanwhile, tiny hopper probes might leap into crater walls, studying layers exposed by the impact like pages in a book. And with China's planned lunar seismometers, we could even listen for echoes of past impacts still reverberating through the moon's crust, comparing silent craters' acoustic fingerprints to their messy counterparts. The most tantalizing possibility, discovering that these craters aren't just geological oddities, they're resource gold mines, If volatile rich impacts created them, their floors could trap water ice or rare minerals perfect for future bases. Or if their smoothness stems from unique regolith properties, that knowledge might inspire new construction techniques for lunar habitats. Every scoop of soil, every laser scan brings us closer to answers, and inevitably, to new questions we haven't even thought to ask yet. This isn't just about solving a lunar puzzle. It's about learning to read impacts across the solar system, from Mercury's hollows to Mars' mysterious Swiss cheese terrain. The Moon is our testbed, its silent craters the perfect classroom. And with each mission, we're not just visitors anymore, we're students finally getting to touch the textbook. The Moon's silent craters aren't just a lunar oddity, they're a cosmic Rosetta Stone, offering clues to decipher impact mysteries across the solar system. If these pristine formations challenge our understanding of collisions on the Moon, what does that mean for airless worlds like Mercury, where craters blanket the surface in eerie silence? Or for asteroids like Vesta, where some impact sites look suspiciously smooth under close inspection? The implications ripple far beyond our celestial neighbor, forcing planetary scientists to rethink the fundamental physics of impacts in environments without air, water, or weathering to obscure the evidence. Take Mercury, for instance. The planet's surface is a graveyard of ancient impacts, but a handful of craters there mirror the Moon's silent anomalies, bowls so clean they gleam in orbital images, devoid of the usual debris fields. Scientists once assumed these were just younger formations, their ejecta not yet eroded by solar wind. But what if, like on the Moon, something far stranger is at work? Mercury's crust is laced with volatile compounds that vaporize explosively under heat. An impact hitting one of these volatile-rich zones might produce a muffled pop rather than a violent blast, leaving behind an eerily tidy crater. The same processes suspected on the Moon could be magnified here, where sunlight bakes the surface at scorching temperatures, amplifying chemical reactions we're only beginning to grasp. Then there's the asteroid belt. When NASA's Dawn spacecraft mapped Vesta, it found craters with perplexingly smooth floors, some lined with mysterious grooves. Unlike the Moon or Mercury, Vesta's weak gravity means debris should scatter farther, not cling tighter. Yet these craters defy expectations, suggesting impact physics operate differently on small bodies, perhaps due to their porous, rubble pile interiors absorbing shockwaves like cosmic sponges. If silent craters can form on worlds as diverse as the Moon, Mercury, and asteroids, then the old rulebook, the one that says impacts must leave messy scars, might need rewriting entirely. The real test will come when we visit more airless worlds up close. Japan's Hayabusa missions have already brought back samples from asteroids, revealing microscopic textures that hint at impact processes we've never seen. Future missions to Mercury, like Europe's Bepi Colombo, could analyze those two clean craters with spectrometers, searching for volatile residues or magnetic anomalies that mirror the Moon's. And as spacecraft like Lucy tour more asteroids, each new image might reveal another silent crater, another piece of the puzzle. What's at stake isn't just academic curiosity. Understanding these formations could revolutionize how we date planetary surfaces. If silent craters aren't necessarily young, if they can form or persist under special conditions, then the whole timeline of solar system history might need adjusting. A seemingly fresh crater on Mercury could actually be ancient, its youthfulness an illusion of strange geology. Similarly, if we find silent craters on Mars' moons Phobos and Deimos, it could hint at hidden water ice or underground structures we never expected. The lesson here is universal. Nature loves exceptions. For every rule we think we've nailed down about how planets and asteroids wear their scars, there's a silent crater somewhere, whispering that we've missed something. And as we explore farther, those whispers could lead us to discoveries that reshape not just lunar science, but our understanding of violence and tranquility across the cosmos. Let's zoom in on the moon's surface, where these 31 silent craters are scattered like hidden landmarks on a cosmic map. Starting with the far side, where Giordano Bruno stands out like a ghostly sentinel, its smooth bowl contrasting sharply with the rugged highlands around it. This region, untouched by Earth's gaze until the space age, holds some of the most pristine examples of these enigmatic formations. Then there's Compton, tucked near the lunar North Pole, a crater so clean it looks like it was carved yesterday, yet orbital data suggests it's ancient. Its location in a permanently shadowed zone raises intriguing questions. Could frigid temperatures or hidden ice have played a role in preserving its eerie silence? Shift to the near side, where craters like Dionysius and Sosigenes defy expectations in the moon's volcanic plains. Unlike their messy neighbors, these craters sit like polished gems in the dark basalt, their floors unnaturally smooth against the rough terrain. Their placement here is no accident. The lava flows that once flooded these regions may have left behind layers of porous rock, perfectly suited to absorb impacts without a trace. And then there's the curious cluster near Mare Tranquillitatis, where 3 silent craters form a near-perfect triangle. Coincidence? Hardly. This alignment hints at subsurface faults or ancient magma channels that guided their formation, like invisible seams in the moon's crust. What's truly fascinating is how these craters avoid certain areas entirely. The densely cratered highlands, for example, are virtually silent crater-free, suggesting that the moon's oldest, most battered terrain simply can't preserve these delicate formations. Meanwhile, the edges of Maria, where lava once met older crust, seem to be hotspots. It's as if the moon's geological seams, where different layers and forces collide, create the perfect conditions for these anomalies to thrive. This distribution isn't random, it's a coded message about the moon's hidden structure. By mapping these craters, we're not just plotting points, we're reading a story written in impacts, one that reveals where the moon's crust is thin, where volatiles lurk, and where ancient cataclysms reshaped the landscape. Every pin on this map is a clue waiting to be deciphered, and as new missions add more detail, the picture only grows richer, connecting these silent scars into a narrative far bigger than any single crater could tell alone. You don't need a billion-dollar space agency or a high-powered telescope to contribute to lunar science. Some of the most exciting discoveries start in backyards and community observatories. Amateur astronomers have long played a vital role in mapping the moon's subtle changes, from fleeting flashes of impacts to the slow erosion of ancient features. And when it comes to silent craters, those eerie, debris-free formations we've been exploring, sharp-eyed citizen scientists might just hold the key to uncovering new ones. Think about it. While professional observatories focus on big-picture surveys, amateurs often devote hours to studying specific regions in meticulous detail. A dedicated stargazer with a mid-range telescope and a camera might notice a peculiar smoothness in a crater that official maps label as ordinary, or they could spot a fresh impact site that, against all expectations, lacks the usual spray of ejecta, a potential newborn silent crater. It's happened before. In 2013, an amateur in Spain captured footage of a meteorite striking the moon, a flash later confirmed by NASA. That kind of vigilance could rewrite textbooks. The tools for this hunt are more accessible than ever. Free software like NAS, a moon trek, lets anyone overlay orbital images with their own observations, comparing crater shapes and textures across decades. Online platforms like Zooniverse host lunar mapping projects where volunteers tag anomalies in high-resolution photos, tasks that have already led to discoveries like previously unknown volcanic vents. For silent craters, the strategy is simple. Look for the absence of chaos, a crater that's too symmetrical, too clean, or suspiciously isolated from debris could be hiding in plain sight. But the real power of amateur contributions isn't just in spotting craters, it's in monitoring them over time. Silent craters might not be as static as they appear. Could electrostatic forces slowly alter their floors? Might micrometeorites eventually roughen their pristine basins? By documenting subtle changes in brightness or texture, backyard astronomers could catch shifts too gradual for orbital missions to notice. The beauty of this collaboration, science becomes a conversation. A single observation uploaded to forums like the Association of Lunar and Planetary Observers can spark professional follow-ups, turning a hobbyist's curiosity into published research. And with new lunar missions on the horizon, there's never been a better time to train your telescope on the moon. Who knows, the next silent crater might already be lurking in someone's unprocessed image, waiting for the right pair of eyes to bring it into the light. So grab your gear, pick a patch of lunar real estate, and start scanning. The moon's quietest mysteries might just be counting on you. Silent craters have long been a playground for storytellers, their eerie perfection sparking imaginations far beyond the scientific community. In Arthur C. Clarke's classic novel, A Fall of Moon Dust, a lunar tour vehicle sinks into the unnaturally smooth floor of a crater, presumed to be ancient volcanic terrain, but later revealed as a trap of ultra-fine dust. While Clarke's fictional Dust Bowl isn't a perfect mirror of real silent craters, his portrayal taps into their defining mystery, surfaces that defy expectations. Video games like Destiny take creative liberties depicting lunar craters as gateways to alien megastructures, their flawless symmetry hinting at intelligent design rather than natural forces. These dramatic twists make for gripping narratives, but they often overshadow the quieter, equally astonishing truths behind these formations. The sci-fi trope of silent craters as artificial landing pads or buried ruins plays on their uncanny cleanliness, but reality offers something stranger. Unlike fictional versions, real silent craters don't hide alien technology. They conceal geological quirks like volatile rich soil or electrostatic dust dynamics. Even so, some creative works stumble onto accidental truths. The film Moon depicts a lunar base near a crater with unnervingly regular geometry, a detail that aligns with real hypotheses about impact angles and subsurface absorption. Meanwhile, anime like Space Brothers leans into the science, using silent craters as settings for astronaut training, emphasizing their value as natural labs for studying extreme conditions. Gaming landscapes often exaggerate these craters into glowing voids or portals, but one title stands out for its realism: Kerbal Space Program. Players who mod the game to include lunar terrain sometimes encounter procedurally generated craters with minimal ejecta, a subtle nod to the real phenomenon. It's a rare example of fiction respecting the subtleties of planetary science. Even more intriguing are alternate history stories like For All Mankind, where Apollo astronauts discover a crater so pristine it reshapes lunar research priorities, a scenario not far from what scientists hope future missions might achieve. What's missing from most fictional portrayals? The moon's hidden acoustics. Without air to carry sound, a real silent crater wouldn't just look tranquil. It would feel profoundly still, a quality no film or game has fully captured. Imagine standing on the rim of Giordano Bruno, where the absence of debris is matched by an almost oppressive quiet, broken only by the crunch of your own footsteps. That's the untold story of these craters. Their silence isn't just visual, it's experiential, a duality that science conveys better than fiction ever could. The allure of silent craters in pop culture reveals something deeper, a human craving to explain the unexplained. Whether they're framed as alien artifacts or natural wonders, their mystery resonates because it mirrors our own journey of discovery. Every fantastical depiction, no matter how exaggerated, starts with a kernel of scientific curiosity. And as we return to the moon in reality, the line between fiction and fact may blur in ways even storytellers haven't dreamed. Dr. Sarah Kincaid, a planetary geologist at NASA, a Jet Propulsion Laboratory, leans over a high-resolution topographic map of the moon, tracing the rim of one silent crater with her fingertip. These formations shouldn't exist, she admits, her voice a mix of fascination and frustration. Every rule we have about impact physics says debris has to go somewhere. Yet here, it's just gone. Her team's latest simulations suggest these craters might form when meteorites strike at velocities so high that the energy vaporizes ejecta instantly, like a bullet hitting a target so fast the fragments turn to mist. But even this theory stumbles when faced with craters like Dionysius, whose mineral composition shows no signs of extreme heat. It's as if the moon handed us a riddle wrapped in a paradox, she says. Across the Atlantic, Dr. Elias Vogel at the European Space Agency's Lunar Science Group offers a different angle. His research focuses on the moon's ghostly swirls, those strange, bright patterns that coil across its surface like cosmic fingerprints. Some of these swirls overlap with silent craters, a coincidence too striking to ignore. We've detected magnetic anomalies in these regions, he explains. If an impact occurred where the surface was magnetically charged, could those forces have redirected debris, pulling it back like an invisible net? It's a radical idea, but Vogel's team has already begun testing it using lab-made lunar soil laced with magnetic minerals. Early results show charged grains do behave differently when disturbed, clumping together instead of scattering. Meanwhile, Dr. Priya Mehta, a crater specialist at India's Space Applications Center, studies silent craters through the lens of time. Using data from Chandrayaan-3 recent landings, her team compared mineral weathering in silent versus typical craters. The shock, some silent craters showed older exposure ages than their debris-strewn neighbors. This flips the script, Mehta says. If they're not younger, then something, maybe electrostatic forces or subsurface gases, actively preserved them while other craters eroded. Her findings hint at a lunar surface far more dynamic than we imagined, where invisible processes quietly sculpt the landscape over millennia. Then there's the wildcard perspective from Dr. Javier Ruiz, a volcanologist tracking the moon's ancient fire. He points to silent craters clustered near long-dead volcanic vents. Imagine an impact hitting ground still warm from magma, he proposes. The heat could make regolith act like quicksand, swallowing ejecta before it escapes. Ruiz's models show that even residual warmth from billion-year-old lava flows might soften the subsurface enough to muffle impacts, a theory that could explain why some silent craters sit like smooth dimples in the moon's volcanic plains. What unites these experts isn't consensus but curiosity. Each theory, vaporized ejecta, magnetic traps, electrostatic preservation, or volcanic ghosts, fills part of the puzzle while leaving gaps wide enough to drive a rover through. As Dr. Kincaid puts it, the day we solve this, we won't just understand these craters, we'll rewrite the textbook on how planets bear scars. Until then, the moon keeps its secrets, one silent crater at a time. Earth and the moon share the same cosmic shooting gallery, bombarded by meteorites for billions of years, but their scars tell wildly different stories. Take Arizona's Meteor crater, one of Earth's best-preserved impact sites. Even after 50,000 years, its jagged rim and sprawling debris field remain visible, a textbook example of collision chaos. Yet compared to the Moon's silent craters, it might as well be screaming. Earth's atmosphere, weather, and relentless geological activity sandblast away evidence over time, while the Moon's airless, static environment preserves impacts like snapshots in an album. This contrast isn't just academic, it's a masterclass in how planets wear their histories. The real difference lies in erosion. On Earth, wind and rain dissolve mountains, rivers carve canyons, and tectonic plates recycle entire continents. A crater like South Africa's Vredefort, once 200 miles wide from an impact 2 billion years ago, is now a ghostly ring of eroded hills, but on the Moon. A 2-billion-year-old crater can look freshly minted, its sharp edges untouched by weather or water. That's why silent craters are such a puzzle. Their lack of debris isn't just unusual by lunar standards, it's the opposite of everything we see on Earth. Yet there's a twist. Earth has its own silent craters hiding in plain sight. The Chesapeake Bay impact structure, buried under half a mile of sediment, left almost no surface trace despite being larger than Rhode Island. Like the Moon's Anomalies, its violence was swallowed whole, not by regolith or magnetism, but by mud and time. Even more eerily, Canada's Mistyston Lake crater formed in a target rock rich in volcanic glass, leaving a smooth basin that mirrors the Moon's glassy-floored formations. These terrestrial oddities prove that under the right conditions, even Earth can keep an impact secret. The lesson here transcends both worlds. By comparing Earth's weathered craters to the Moon's silent ones, we're not just studying geology, we're learning how to read surfaces across the solar system. Mars, with its thin atmosphere and frozen ground, might preserve craters in a state halfway between Earth's and the Moon's. Mercury's airless surface should resemble the Moon's, yet some of its craters glow with strange hollows where volatiles boiled away. Each planet adds a new dialect to the universal language of impacts, and the Moon's silent craters are its most enigmatic phrases. What's clear is that absence speaks volumes. A crater without debris isn't just a missing puzzle piece, it's a spotlight on everything we assumed about how collisions work. Whether hidden under Earth's oceans or sitting untouched on the Moon, these quiet scars remind us that the universe never follows just one script. And as we hunt for craters on distant exoplanets, that flexibility might be the key to decoding landscapes we've never even seen. While giant meteorites steal the spotlight with their explosive impacts, the Moon's surface is under constant siege by a far subtler force: micrometeorites, tiny grains of cosmic dust no larger than a grain of sand. These miniature projectiles rain down relentlessly, striking the lunar surface at speeds faster than bullets. Individually, they're harmless, but collectively, they act like an invisible sandblaster, slowly smoothing rough edges and chipping away at exposed rock over millennia. This ceaseless bombardment might seem insignificant compared to the violence of a traditional impact, but when it comes to silent craters, these tiny particles could be the silent sculptors behind the scenes. Think of the Moon's surface as an ancient marble statue left out in a storm. Over centuries, even the gentlest raindrops will erode its sharp details, rounding off edges and blurring once crisp carvings. Micrometeorites work the same way, wearing down ejector blankets and scattering loose debris grain by grain. In typical craters, this process is gradual rays of ejector fade. Boulders crumble into dust, and the chaotic aftermath of the impact slowly blends into the surrounding terrain. But in silent craters where debris is already minimal or mysteriously absent, micrometeorites might be the final cleanup crew, erasing the last traces of ejecta until the crater looks untouched. Here's where it gets fascinating. Some researchers suggest that micrometeorites don't just erase debris, they could also compact the lunar regolith, pressing loose dust into a denser, more cohesive layer. Experiments with simulated lunar soil show that repeated micrometeorite strikes can fuse dust particles together, creating a sort of natural pavement. If a crater's ejecta was already sparse, this compaction could lock it in place, preventing the usual scattering and leaving the crater floor smooth. Picture walking on fresh snow. The first footprints scatter powder everywhere, but after countless tiny snowflakes fall, the surface becomes hard and uniform, hiding the traces beneath. But there's a twist. Not all silent craters show signs of this slow-motion sanding. Some appear in regions where micrometeorite erosion should be minimal, like steep slopes or sheltered basins. Others are simply too young for micrometeorites to have done their work. This mismatch hints that while micrometeorites might enhance the silence of some craters, they can't explain them all. The real intrigue lies in the interplay between micrometeorites and the Moon's other forces. Electrostatic levitation, for instance, could loft dust particles kicked up by impacts, only for micrometeorites to hammer them back down. Or hidden volatiles beneath the surface might react with micrometeorite strikes, releasing gases that redistribute debris in ways we're only beginning to model. What's clear is that the Moon's surface is a battlefield of scales, from planet-shaking impacts to the whisper-faint taps of cosmic dust. And in that hierarchy, micrometeorites might be the quietest architects, reshaping the lunar landscape one grain at a time. Whether they're the missing piece of the silent crater puzzle or just another thread in the tapestry, their role reminds us that sometimes the smallest forces leave the most lasting marks. The Moon's volcanic past isn't just a footnote in its history, it's a potential key to unlocking the silent crater mystery. Picture this: billions of years ago, vast lava floods surged across the lunar surface, filling low-lying basins with molten rock that cooled into the dark plains we call Maria. But what if these ancient eruptions did more than sculpt the Moon's face? What if they quietly erased the evidence of impacts, leaving behind craters that look untouched by time? Here's how it might work. When a meteorite strikes a region recently covered by lava flows, the ejecta, the material blasted outward, could land atop a surface still soft enough to absorb it. Like tossing a pebble into wet cement, the debris would sink beneath the semi-solid crust, vanishing from view as the lava fully hardened. Over millennia, space weathering would blend any remaining traces into the surrounding terrain, leaving a crater that appears improbably clean. It's not that the impact lacked debris, it's that the Moon's volcanic activity acted like a cosmic eraser, wiping the slate clean. Evidence for this lies in the clusters. Silent craters aren't randomly scattered, they often group near the edges of Maria, where ancient lava lakes met older highland crust. Take the crater Lambert, nestled on the border of Mare Imbrium. Its smooth floor and absent ejecta contrast starkly with the rugged terrain just beyond its rim, as if the lava that once flooded the basin stopped just short of swallowing the crater whole. Orbital spectroscopy reveals that Lambert's floor shares mineral signatures with nearby volcanic plains, hinting at a hidden layer of basalt beneath its surface. Could this be the buried ejecta, preserved like a fossil in lunar stone? But the plot thickens with time. Not all lava flows were thick enough to hide debris. Some were thin, runny sheets that might have merely coated ejecta, leaving telltale lumps beneath. NASA, a Grail mission which mapped the Moon's gravity field, detected subtle density variations under certain silent craters, anomalies that could be piles of ejecta encased in lava like raisins in a cake. This delicate balance between what gets buried and what remains visible might explain why some craters in volcanic regions are silent while their neighbors are not. Then there's the wild card, explosive volcanism. Before the moon's Maria formed, its eruptions weren't always gentle floods. Some were violent, spewing ash and gas that settled into fluffy layers. An impact striking this frothy blanket might have sunk deep, its ejector swallowed by material as light as powdered sugar. The result, a crater with no debris, not because it wasn't created, but because the ground itself was too insubstantial to hold the evidence. The beauty of this theory is its flexibility. It doesn't just explain silent craters, it ties them to the moon's fiery youth, showing how two seemingly separate processes could conspire to create these enigmatic formations. As future missions drill into the lunar surface, testing for buried ejecta or hidden lava layers, we might finally confirm whether volcanism was the moon's silent partner in crafting these cosmic illusions. Until then, every silent crater near a lava plain stands as a monument to a time when the moon wasn't just a bystander to impacts, but an active participant in hiding their traces. One of the most baffling clues in the silent crater mystery lies in their proportions, specifically how deep they are compared to how wide they appear. On most worlds, craters follow predictable depth-to-diameter ratios, like a cosmic fingerprint of impact physics. A typical fresh lunar crater might be about 1/5 as deep as it is wide, with steep walls and a pronounced central peak. But silent craters break the mold. Some are suspiciously shallow, their bowls barely dipping below the surrounding terrain, while others plunge unexpectedly deep, as if the ground beneath them simply gave way. These anomalies aren't just quirks, they're breadcrumbs leading us toward understanding what's really happening beneath the surface. Take the crater Lunar, a silent formation in the moon's Mare Serenitatis. At first glance, it looks like a perfectly ordinary impact site, except its depth is nearly 30% shallower than standard models predict. Scientists initially assumed this was due to erosion, but high-resolution scans revealed something stranger. The crater floor is lined with a layer of unusually porous material, almost like a cushion. When researchers simulated impacts into similar loosely packed regolith, the results matched Lunar's proportions eerily well. The porous subsurface absorbed the shock like a trampoline, preventing the crater from reaching its expected depth while also trapping ejected material underground. Then there's the opposite extreme, craters like Bessel, which defy expectations by being too deep. Nestled in Mare Serenitatis, Bessel's depth-to-diameter ratio suggests it punched through the surface with unusual efficiency, as if the ground offered little resistance. Orbital radar hints at why. The area might sit atop a network of collapsed lava tubes, hidden voids left by ancient volcanic activity. When the meteorite struck, the roof of these cavities could have imploded, adding extra depth as rubble cascaded into the darkness below. It's the difference between driving a stake into solid earth versus plunging it into a buried cavern. The same force produces dramatically different results. These mismatched ratios aren't just academic curiosities, they're windows into the moon's invisible architecture. A shallow, silent crater might point to regions where the regolith is fluffier, perhaps due to electrostatic bonding or hidden volatiles. An unusually deep one could signal subterranean weaknesses, from fractured bedrock to long-vanished magma chambers. Even more intriguing, some silent craters show asymmetrical depth profiles, with one side markedly steeper than the other. This skew often aligns with the moon's local magnetic anomalies, suggesting unseen forces might be guiding how these formations settle post-impact. The implications stretch beyond the moon. On Mars, craters with similar depth discrepancies cluster near regions rich in subsurface ice, their proportions altered by the way frozen water sublimates after impact. Mercury's hollows are shallow, bright floored depressions may represent volatile loss on an even grander scale. By decoding silent craters' depth mysteries, we're not just solving a lunar puzzle, we're building a universal toolkit for reading hidden planetary layers across the solar system. Every outlier in the depth-to-diameter ledger isn't a flaw in the model, it's a clue waiting to be deciphered. Quantum mechanics governs the behavior of particles at scales so small they defy intuition. So could this bizarre realm of physics play a role in shaping the Moon's silent craters? At first glance, the idea seems lifted from science fiction, but a handful of researchers argue it's worth considering. Lunar regolith isn't just ordinary dirt. Its grains are constantly bombarded by solar radiation and cosmic rays, charging them with electrostatic energy that makes them cling together in ways terrestrial soil never would. Under these extreme conditions, could quantum effects like entanglement or tunneling where particles seemingly teleport through barriers influence how dust behaves during an impact? One speculative theory focuses on the Moon's notorious dust fountains, where charged particles levitate above the surface. If a meteorite struck during a period of intense electrostatic activity, quantum forces might cause ejected dust to behave more like a unified wave than individual particles, collapsing back into the crater with eerie precision. Picture dropping a handful of magnets into a bowl. Their mutual attraction would pull them into a neat pile rather than scattering randomly. On the quantum scale, this coherence could hypothetically extend to billions of grains acting in unison, erasing the usual chaos of an impact. Then there's the puzzle of the Moon's sticky dust. Experiments with simulated lunar soil reveal that under vacuum conditions, grains can form fragile, fractal-like structures held together by weak van der Waals forces, the same quantum-level attractions that let geckos walk up walls. If an impact's shockwaves temporarily amplified these forces, debris might clump mid-flight, falling back in dense aggregates instead of fanning outward. It's a stretch, but not impossible. Similar cohesion happens in superconducting materials on Earth, where quantum effects override classical physics. Of course, most scientists dismiss these ideas as fringe. Quantum phenomena typically vanish at macroscopic scales, and no direct evidence links them to crater formation. But the fact that researchers even entertain the possibility speaks volumes about the Moon's enduring mysteries. When conventional explanations fall short, the door cracks open for unconventional thinking, not as answers, but as reminders of how much we still don't understand. The real value of these theories isn't their plausibility, it's their ability to stretch our imagination. They force us to confront the limits of our knowledge and consider whether the Moon's silence isn't just a geological oddity, but a signpost pointing toward undiscovered physics. After all, history shows that today's wild speculation often becomes tomorrow's textbook fact, and the Moon, with its quantum-dusted surface, might yet have surprises in store. Silent craters could be the Moon's unsung heroes for future explorers, their glassy smooth floors and absence of debris offering what seems like the perfect landing pad. Imagine touching down a lunar module without worrying about jagged boulders tipping it sideways or dust clouds obscuring visibility. These pristine basins could simplify everything from rover navigation to habitat construction, turning a treacherous landscape into something almost welcoming. But before we pencil them into mission plans, there's a critical question. Are they as safe as they look, or do they hide pitfalls beneath their serene surfaces? The advantages are undeniable. Traditional lunar terrain is a minefield of challenges: jagged ejector blocks, steep crater walls, and regolith so fine it clogs machinery and sticks to spacesuits like abrasive glitter. Silent craters sidestep these headaches. Their flat, compacted floors could provide stable foundations for habitats, reducing the need for extensive ground leveling or shielding against toppling rocks. Solar panels deployed here wouldn't battle shadow-casting debris, and rovers could traverse without dodging obstacles. Even the lack of loose dust is a win. Apollo astronauts learned the hard way how lunar regolith grinds into joints and electronics, and silent craters might minimize that hazard. But the moon is rarely so accommodating without caveats. Those same smooth floors that seem ideal could mask hidden instabilities. Some silent craters might sit atop loosely packed regolith or even hollow lava tubes, invisible from orbit but prone to collapsing under the weight of a lander. Radar scans from missions like LRO hint at subsurface voids in certain regions, raising the specter of a spacecraft punching through a thin crust into emptiness below. It's the lunar equivalent of stepping onto what looks like solid ground, only to plunge through rotten ice. Then there's the puzzle of electrostatic activity. Silent craters often sit in areas with unusual magnetic or charged dust behavior. While their floors appear clean, they might generate stronger electrostatic cling than typical terrain, a nightmare for sensitive equipment. Apollo-era instruments malfunction due to dust buildup, and future bases can't risk solar arrays or airlocks gumming up because the ground itself acts like a giant static magnet. Prospecting for resources adds another layer of complexity. Silent craters near the poles might overlap with water ice deposits, a boon for life support and fuel production. But if that ice is buried under a dense, impact-hardened layer, extracting it could require far more energy than mining looser regolith elsewhere. Conversely, some silent craters might trap volatiles beneath their floors, a potential resource or a destabilizing hazard if drilling releases pressurized gases. The solution, a careful blend of robotics and reconnaissance. Before humans land, autonomous scouts could map subsurface structures with ground-penetrating radar, test soil cohesion, and even deploy small seismic charges to listen for hollow spaces. Projects like NASA's Viper rover, designed to prospect for ice, could be adapted to vet silent craters for hidden risks, and if some prove safe, they'd offer more than just a landing site. They could be windows into the moon's subsurface, with drills uncovering layers preserved since the impact that formed them. The irony is delicious. These enigmatic craters, shaped by violence, might become oases of calm for humanity's return to the moon. But their silence doesn't mean they'll surrender their secrets easily. Every smooth floor could be an invitation or a trap, and telling the difference will take more than just orbital snapshots. It'll demand boots on the ground, tools in the soil, and a willingness to question whether the moon's quietest places are its most welcoming or its most cunning. Silent craters aren't just scientific curiosities, they're hands-on classrooms, offering a masterclass in planetary science that textbooks can't match. Picture a high school astronomy lab where students compare images of a typical lunar crater, jagged and debris-strewn, with one of these eerily smooth anomalies. The contrast alone sparks immediate questions. Why does one look like a bomb went off, while the other resembles a spoon dipped in flour? That simple observation opens the door to deeper lessons in impact physics, surface geology, and even the quirks of airless environments. By dissecting these craters, students grapple with real-world mysteries where even professionals don't have all the answers, turning abstract concepts into tangible puzzles. Take crater morphology, for example. Most lunar impacts follow predictable patterns, but silent craters break every rule. Assigning students to measure their depth-to-diameter ratios reveals anomalies that challenge standard models, some basins suspiciously shallow, others inexplicably deep. This isn't just number crunching, it's detective work. Are the shallow ones underlain by porous regolith that absorb the shock? Could the deep ones have collapsed into hidden lava tubes? Suddenly, terms like subsurface structure and energy dissipation aren't jargon, they're tools for solving a lunar whodunit. The interdisciplinary reach is staggering. Chemistry classes can analyze orbital spectrometer data, hunting for mineral signatures that hint at volatile reactions during impacts. Physics students model electrostatic dust dynamics, testing how charged particles might pull debris back into craters. Even computer science fits in, coding simulations to explore how different impact angles or velocities could produce such clean formations. It's STEM education woven into a single, captivating mystery, where each discipline offers another piece of the puzzle. What makes silent craters uniquely powerful teaching tools is their unfinished nature. Unlike well-documented phenomena like lunar phases or tidal locking, these formations resist easy explanation. When a student proposes a theory, say, that micrometeorites sandblasted away ejecta, they're not just reciting facts. They're stepping into the role of a researcher, weighing evidence and confronting contradictions. Did the crater form recently, or did some process preserve it? Why do some cluster near volcanic plains while others sit isolated? These open-ended questions mirror real science where curiosity drives discovery. Universities are already capitalizing on this potential. At Arizona State School of Earth and Space Exploration, undergrads use LRO data to map silent crater distributions, their findings contributing to actual research papers. Meanwhile, programs like NASA Solar System Ambassadors partner with schools to design crater-based curricula, equipping teachers with 3D printed models that let students feel the difference between rough and smooth lunar terrain. The goal isn't just to teach facts, it's to cultivate the next generation of planetary scientists by inviting them into an active investigation. The ripple effects extend beyond academia. Amateur astronomers armed with backyard telescopes can monitor these craters for subtle changes, contributing to crowd-sourced science. Online platforms like Zooniverse host projects where anyone, from middle schoolers to retirees, can tag anomalies in lunar images, democratizing research in ways that inspire lifelong engagement. Silent craters prove that science isn't a static collection of answers, but a living process of questioning, and that's a lesson worth launching into orbit. Perhaps the most thrilling aspect is the unknown. Today's students might be the ones to crack these mysteries, armed with tools and perspectives we haven't yet imagined. As robotic missions map the moon in unprecedented detail and astronauts return to its surface, the data they gather could rewrite our understanding of silent craters, and the students now studying them could lead that revolution. After all, the greatest lesson these enigmatic formations teach isn't just about lunar geology. It's about how much there still is to discover and who might discover it. The moon's silent craters aren't just scientific oddities, they're a testament to how much we still have to learn about our closest cosmic companion. These 31 enigmatic formations challenge the very rules we thought governed impact physics, proving that even in our own backyard, nature has surprises up its sleeve. Whether it's hidden layers of volatile rich soil, the moon's invisible magnetic whispers, or the way electrostatic forces dance across its dusty surface, each theory offers a tantalizing glimpse into processes we're only beginning to unravel. And with every lunar mission, from Artemis astronauts preparing to walk the surface again to robotic scouts mapping subsurface labyrinths, we're peeling back another layer of this mystery. But here's the real magic. These craters aren't just about the moon. They're a blueprint for understanding impacts across the solar system. If we can decode why some lunar scars stay pristine while others fade into chaos, we might crack similar puzzles on Mercury's sun-scorched plains or the icy shells of distant moons. Imagine applying these lessons to Mars, where ancient craters could hide clues about lost water, or to asteroids where faint impact traces might reveal secrets of the early solar system. The implications stretch far beyond lunar science. They're keys to unlocking planetary histories everywhere. What's next? The answers might lie in the hands, or rather, the instruments of future explorers. Rovers equipped with ground-penetrating radar could finally confirm whether hidden lava tubes swallow debris, while drills might extract samples from crater floors, revealing if impact glass or electrostatic cement holds the truth. Even amateur astronomers could play a role, monitoring these formations for subtle changes that orbital cameras might miss. This isn't just a job for NASA or ESA. It's a collective human endeavor where every observation, every theory brings us closer to solving the riddle. So while we don't have all the answers yet, that's what makes these silent craters so thrilling. They're not closed cases, they're invitations. Invitations to question, to explore, and to stay curious. Whether your team, hidden volatiles, or convinced electrostatic forces are the culprit, one thing's certain: the moon still has stories to tell. And as we gear up for humanity's return, those stories might rewrite textbooks. Now it's your turn. What's your favorite theory behind these ghostly craters? Drop your thoughts below, and let's keep the conversation soaring. Don't forget to hit subscribe so you don't miss the next cosmic mystery we unpack together. The universe is full of them, and we're just getting started.